Since we understand how we use the FGK model to generate or produce protein sequence motifs, it is time for us to see how do we use those motifs to predict the protein local tertiary structure. So if we take a look of the original FGK model, the original data set is going to be used by fuzzy sequence clustering to softly cut into 10 information granules. For each information granule, we use the greedy k-means clustering to find the protein sequence motifs, and basically we try to join the information together. By looking into their secondary structure similarities, we can find some high quality protein sequence motifs. So that is what we discussed in basically chapter 1 and chapter 2 of the thesis. Now, in chapter 3, we expand this whole structure into a bigger picture. So let's take a look of this one to see what is happening. It's basically very similar structures that what we see over here, except that we add a decision forest area. So try to map the original picture into this chapter. The original data is the original data set, which is composed of the PICES that we select 2,710 proteins, looking into their HSSP, which is the protein primary sequence profiles, and then add with DSSP, finding the secondary structure information using the sliding window technique, and we of course also add the tertiary structure information, and so that we generate the original data set. For the original data set, we try to use the fuzzy sequence clustering to cut into the smaller information granules and then apply the k-means clustering to generate the protein sequence motifs. So you can see that the original data set goes with all the processing and then through the FGK model ends in here. Now in this chapter, we add the decision tree concepts over here to walk through each protein sequence motifs. We basically try to filter out that the elements that does not belong into the motifs, and then we use the training data to look into combine with the decision forest that we generate and make the prediction. Of course, we want to look a little bit deeper into this area. So you should already know about the decision tree through my data mining class already. So in this example is saying that throughout the whole data set, it has built up a decision tree, and the question or the label is that we try to go to walk or not to walk. And then after all of the processing, try to find the entropy and calculate information gain, we realizing that the first node, which is the root of the decision tree, is it raining? If it's yes, then go to this side of the tree. If no, then go to this side of tree. So basically you can see that the data that we have been trained, or the attribute that we have been trained, is actually a binary data set, yes or no. So if it is raining, and do I need the exercise? If it's no, then basically don't go to walk. If we need to do some exercise, then ask, do I have an umbrella? If it's yes, then go to a walk. If no, then do not go to a walk. You can see that the umbrella is attached with the information about the raining. And therefore, on the left side of the decision tree is based on the raining scenario. On the other side, it's not raining, and then we try to check the temperature. If it's a good temperature, then go for a walk. If it is hot, then we try to ask, we have a water bottle. We want to get us hydrated. We don't want to get a dehydrated situation, and based on that information, we can decide to go to walk or not to walk. So this is the basic idea of the decision tree. Now, how do we add this decision tree into the motif information, and how do we use that to predict protein local tertiary structure? Let's take a look of it. Decision tree in our data set. So think about this. in our FGK model, we try to evaluate the protein sequence information through the secondary structure similarity. So if the secondary structure similarity of the cluster exceeds 70%, we then consider it structurally identical. On the other side, even it's in between 60 and 70 similarities, we still consider it as a weakly structural homology. In other words, if we use 70% as the threshold to determine a good cluster or a bad cluster, even it is a good cluster saying that it satisfies 70% of the secondary structure similarity, there's still possibility that about 30% of the segments that are actually not really having the identical structure, because we use clustering to group all the things based on their primary sequence together. However, not all of them share the same secondary structure. And therefore, what we want to do is that it is possible for each cluster, and remember we have a lot of clusters, we have like 799 clusters. For each cluster, we can build a tree to determine when a sequence comes into this cluster, saying that we try to find the closest distance. We find the cluster and we can feed into the tree and then see if this segment belongs to this cluster or not. If it belongs, then we can use this cluster's 3D structure to predict the 3D structure of unknown segment, which is our testing data set. If it is not belonging to this tree, then you should try another tree so that when it comes to the closest one, then we just don't predict the 3D structure using this cluster's 3D structure. We use the next closest one or the next closest one until it finds the tree that belongs to it. And therefore, this is the idea of how we can use the decision tree into the cluster of the protein sequence motifs. Here is one example of the decision tree for a motif. So you can see that in this cluster, the first node that you want to look into is at the position of 69. Remember that we have a window size of 9, and each window size has 20 amino acids probability. So in primary sequence wise, we have 180 dimensions over there. This is saying that the 69th dimension, we try to see if it is, for the testing data set, in the 69th location, if it's between 0 to 4, then it is not belonging to this cluster. If it's 5 to 7, it is not belonging to this cluster. However, if it is 8 to 14, then we try to look into other choices. If it is 15 to 29, this is another subtree. And then if the value is between 30 to 100, then you try another tree over here. So you can see that the whole decision tree concept is applicable into the protein sequence motifs. The difference is that for each attribute, we look into, instead of 2 range of the values, there are 5 different ranges of the values, and that's what we have found more interesting in this bioinformatics application. The range is decided by the experts of the field, so that they think 5 ranges is actually a more reasonable than, of course, 0 to 50, 50 to 100. And therefore, this is the idea of the protein sequence motifs applied with the decision tree to see if this segment belonging to this cluster or not. So basically, we add one more layer of the filter. In my other research, the easiest way, and we will see the result, is that if the testing data compare with all the clusters, as long as they find the closest one, we use the closest one to make the prediction. That's of course very straightforward. Now we add one more layer of the decision tree to see if this segment really belongs to this motifs. So that is the idea of how we will be able to make the predictions. So to look into some parameter setup for the whole experiment, we have set up for fuzzy C-means clustering, we have the falsification factor set to 1.05, and then the window size, of course, is 9 as we choose. The secondary structural similarities threshold by the greedy K-means clustering, we have several settings over here. We have some clusters between 80% to 100% similarity. That is, of course, the best cluster or the best motifs that we can find. And there's something between 79 to 75, 74 to 70, so that if you remember correctly, up to this point, all of these clusters are considered structural homology. So they are great examples of using to predict the protein 3D structures. For the rest part of it, they are less interesting. So those are the things that we are less using in the form to the prediction. So, and the number of information granules and cluster are set to 10 and 799 respectively. And of course, the range that we used is between 0 to 4, 5 to 7, 8 to 14, 15 to 29, and 30 to 100.